Welcome back to Things I Know Nothing About, the podcast where we dive deep into complex topics and try to make sense of them, even if we start from zero. Today, we're tackling a really concerning subject that hits close to home for many, especially those in agricultural communities, a common pesticide linked to an increased risk of Parkinson's disease.
It's one of those headlines that immediately grabs your attention, isn't it? Pesticide giving people Parkinson's. It sounds incredibly alarming and honestly a bit terrifying. But as always, we're going to peel back the layers, look at the actual science, and try to understand what this really means beyond the initial shock value. We want to understand the nuances, not just the scare factor.
Absolutely. And today's discussion centers around a specific pesticide called chlorpyrifos, which has been incredibly widely used in U.S. agriculture for decades. The catalyst for our conversation is a significant March 2026 UCLA health study that found a more than 2.5-fold increase in Parkinson's disease risk for individuals with long-term exposure. That's a pretty stark number right there, prompting us to ask, how solid is this evidence and what's the full picture?
Exactly. So let's start with that UCLA health study because it really is the backbone of this current discussion. It was published in the journal Molecular Neurodegeneration, which is a reputable publication, and it didn't just look at correlations, it combined different types of evidence to build a stronger case. They looked at human epidemiological data and also conducted laboratory experiments, which is a really robust approach when you're trying to establish a likely causal link.
That multifaceted approach is really key, isn't it? When you have both population-level data and mechanistic insights from lab work, the argument for causation becomes much more compelling. The human epidemiological component of the study was a case control analysis, which means they compared a group of people with Parkinson's to a similar group without the condition. This particular study drew its participants from UCLA's Parkinson's Environment and Genes, or PEG study, which is a well-established cohort.
Yes, and the numbers are quite substantial for a study like this. They included 829 people diagnosed with Parkinson's and 824 individuals without the condition, which gives it a good statistical power. What's particularly impressive about their methodology is how they estimated exposure. They didn't just ask people if they remembered being exposed to pesticides, they linked California pesticide use records, which date all the way back to 1974, to the participants' residential and workplace locations over many years. That is an incredibly detailed and precise way to quantify long-term exposure.
That's really crucial for accuracy because self-reported exposure can be unreliable, and recalling specific chemical exposures from decades ago would be nearly impossible. By using actual pesticide application records and geocoding them to participants' addresses over such a long period, they were able to create a much more objective and reliable measure of cumulative exposure. This kind of historical data linkage allows researchers to assess what long-term exposure truly means in a real-world context, rather than just relying on current snapshot data, which is often a limitation in environmental health studies.
And the findings from this epidemiological part of the study were quite striking, as you mentioned. They found that individuals with long-term residential exposure to chlorpyrifos had more than a 2.5-fold greater likelihood of developing Parkinson's disease compared to those with little or no exposure. But it didn't stop there. For those with the highest cumulative workplace exposure, the risk was even higher, rising to 2.74 times. This distinction between residential and occupational exposure is important because it speaks to different levels and durations of contact with the chemical.
Indeed, the distinction between residential and workplace exposure often correlates with the intensity and duration of contact. Farm workers, for instance, might experience direct, high-level exposure during application or re-entry into treated fields, whereas residential exposure might be more diffuse through drift or residues in the environment. Dr. Jeff Bronstein, a professor of neurology at UCLA Health and the study's senior author, emphasized that this study establishes chlorpyrifos as a specific environmental risk factor for Parkinson's disease, not just pesticides as a general class. That's a really important nuance, pinpointing one specific chemical among many, which helps narrow down the focus for both research and regulatory action.
And that brings us to the second, equally important part of the study: the laboratory findings, which provide biological plausibility. It's not enough to say these people were exposed and they got sick. You also want to understand how the chemical might be causing the disease. The UCLA researchers used animal models, specifically mice and zebrafish, to investigate the mechanisms. This is where they moved beyond correlation and started looking for the underlying biological processes, which really strengthens the overall conclusion.
Absolutely. They exposed mouse models to aerosolized chlorpyrifos for 11 weeks, which was designed to mimic human inhalation exposure, a common pathway for environmental contaminants. The results in these mice were quite concerning. They developed movement problems, which is a hallmark symptom of Parkinson's, and critically, they lost dopamine producing neurons. Dopamine neuron degeneration in a specific brain region called the substantia nigra is the primary neuropathological feature of Parkinson's disease, so seeing that directly in the mouse model is a very strong indicator.
Not only that, but the mice also showed brain inflammation and an abnormal accumulation of alpha-synuclein, which are two other key pathological features of Parkinson's disease. Alpha-synuclein is a protein that misfolds and aggregates in the brains of Parkinson's patients, forming what are called Lewy bodies, and these contribute significantly to neuronal dysfunction and death. So, the fact that chlorpyrifos exposure in mice replicated these specific markers of Parkinson's pathology is powerful evidence for a causal link. It's like hitting all the major checkpoints on the disease's biological signature.
And then moving to an even finer level of detail, the experiments in zebrafish further revealed a specific cellular mechanism. They found that chlorpyrifos damages neurons by disrupting autophagy, which is essentially the cell's cleanup system. Autophagy is responsible for clearing out damaged proteins and organelles, kind of like a cellular recycling program. If this system is disrupted, waste products, including misfolded proteins like alpha-synuclein, can build up, leading to cellular stress and ultimately neuronal death.
That's a really elegant piece of the puzzle, because it shows how the pesticide might be causing the accumulation of alpha-synuclein and the subsequent neurodegeneration. They even went a step further, demonstrating that restoring autophagy or eliminating synuclein reduced neuronal vulnerability in these zebrafish models. This suggests potential pathways for intervention or even treatment down the line, although that's a much longer-term prospect. But for establishing a causal link, showing the how through these mechanisms is incredibly compelling and moves the understanding beyond just statistical association.
It truly does. And it's worth noting that the study acknowledged funding from reputable sources like the Levine Foundation and the NIH, and the authors explicitly declared no competing interests. This transparency is important, as funding sources can sometimes raise questions about bias, but in this case, it appears to be a well-supported and independently conducted piece of research. This comprehensive approach, combining robust human epidemiology with detailed mechanistic studies in animal models, really solidifies the claim that chlorpyrifos is not just another general pesticide, but a specific environmental risk factor for Parkinson's.
Now, this more than 2.5-fold increase in risk sounds incredibly dramatic, and it is, but it's crucial to understand the difference between relative risk and absolute risk. This is where headlines can sometimes be a bit misleading, not because they're wrong, but because they often present relative risk without the full context of absolute risk, which can make things sound scarier than they are in terms of individual probability. We really need to clarify what these terms mean to understand the true impact.
That's a really important distinction, Maya, and it's something we always try to emphasize on this show. Relative risk tells you how much more likely an exposed group is to develop a disease compared to an unexposed group. So, in this case, people with long-term chlorpyrifos exposure were 2.5 times more likely to get Parkinson's. It's a measure of the strength of the association between the exposure and the outcome. It's a very real and significant finding, but it doesn't tell you the overall chance of getting the disease.
Right? And that's where absolute risk comes in. Absolute risk is the overall chance of developing the disease in a given population over a certain period. It's the actual probability. So, even if the relative risk is high, if the baseline absolute risk of a disease is very, very low, then a 2.5-fold increase might still mean a relatively low absolute chance for any single individual. However, for a widespread disease like Parkinson's, even a modest increase in absolute risk across a large population can translate into many more cases.
Let's put some numbers to that for Parkinson's disease specifically. Parkinson's affects approximately 1 million Americans with about 90,000 new diagnoses annually. Globally, over 8.5 million individuals had Parkinson's in 2019, and the age standardized incidence rate was about 15.63 per 100,000 population in 2021. The lifetime risk of Parkinson's for the general population is estimated at about 6.6%. These are not insignificant numbers. It's a condition that affects a substantial portion of the population.
So let's try to illustrate this with a hypothetical example to really make it concrete. If the baseline absolute risk of Parkinson's in an unexposed population over a certain period were, let's say, 1 in 1,000, then a 2.5-fold increased relative risk would mean the exposed population has an absolute risk of 2.5 in 1,000. While the relative risk of 2.5 times is significant from a clinical and public health perspective, the absolute numbers help contextualize the overall probability for an individual. It means that while your individual chance still seems small, the factor by which it's increased is quite large, and that's what makes it concerning, particularly when thinking about public health interventions.
Exactly. It's not saying that if you're exposed, you will get Parkinson's, but it significantly elevates your chances compared to someone who isn't exposed. And when you consider the sheer number of people potentially exposed to chlorpyrifos over decades, even a relatively small increase in absolute risk per individual can translate into a substantial number of additional Parkinson's cases across the population. That's why identifying a specific environmental risk factor like this, even if it doesn't guarantee the disease, is incredibly important for public health initiatives and prevention strategies.
This distinction is really important because it helps us avoid both panic and complacency. We're not saying everyone exposed is doomed, but we are acknowledging a very real and statistically significant increase in risk that contributes to the overall burden of the disease. It emphasizes that while Parkinson's is a complex disease with multiple contributing factors, chlorpyrifos is emerging as a specific, identifiable environmental risk that we can and arguably should do something about. This brings us squarely into the long and contentious regulatory history of chlorpyrifos with the Environmental Protection Agency, or EPA.
And what a history it is. Chlorpyrifos was first registered way back in 1965 by Dow Chemical Co., and quickly became one of the most widely used organophosphate pesticides in the US it was, and in some places still is applied to a vast array of crops, including corn, soybeans, fruits like apples and oranges, and nuts. Its effectiveness as an insecticide made it a staple in agriculture, which is part of why its regulation has been such a battleground for so long. The economic stakes are incredibly high for many farmers in the industry.
The first major regulatory action came around 2001 after growing concerns about potential risks to children. The EPA reached a voluntary agreement with the pesticide registrants to eliminate most residential uses of chlorpyrifos. This was a response to evidence suggesting that children, due to their developing brains and higher exposure relative to body weight, were particularly vulnerable to the neurotoxic effects of organophosphates. It was a step in the right direction, acknowledging a problem, but it left agricultural uses largely untouched.
And that's a critical point, Maya. While getting it out of homes was a win for children's immediate exposure, it didn't address the broader issue of agricultural drift or residues on food. Then, in 2012, the EPA took another step, lowering aerial pesticide application rates and creating no-spray buffer zones around public spaces like schools and homes. This was an attempt to further protect children and bystanders from direct spray drift, acknowledging that even if it wasn't being sprayed in their yards, it could still reach them from nearby fields.
But even these measures weren't enough for many public health advocates, and for good reason. Between 2015 and 2017, EPA scientists, drawing on an accumulating body of evidence, including studies linking prenatal exposure to neurodevelopmental harm in children, proposed revoking all food tolerances for chlorpyrifos. This would have effectively banned its use on food crops entirely, based on the determination that there was no safe level of residue in food, especially for children. This was a significant move, signaling a shift in the scientific understanding within the agency itself.
However, the regulatory pendulum swung dramatically in 2017. Under a new administration, the EPA reversed course, denying a petition to ban chlorpyrifos. Their stated reason was scientific uncertainty, and they deferred further review until 2022. This decision was met with widespread criticism from environmental and public health groups who argued that the existing scientific evidence was more than sufficient to warrant a ban. It highlighted the highly politicized nature of chemical regulation, where scientific assessments can be overridden by policy decisions and industry pressure.
This scientific uncertainty argument is a classic tactic used by industries to delay regulation, often by demanding an impossibly high standard of proof for harm, while downplaying the precautionary principle. The existing evidence, even before the 2026 UCLA study, was already pointing to significant risks, especially for children's developing brains. This reversal meant that chlorpyrifos continued to be used on food crops for several more years, perpetuating exposure for millions.
Fast forward to 2021, and the situation changed again. Following a court order, the EPA issued a final rule revoking all chlorpyrifos tolerances on food, effectively banning its use on food crops. This was largely seen as a major victory for public health and environmental advocates who had been fighting for this for years. The court's intervention underscores the legal pressure that can be brought to bear when regulatory agencies are perceived as failing to protect public health based on available scientific evidence. It truly felt like a definitive end to the saga for many.
But the story doesn't end there, demonstrating just how complex and entrenched these battles are. In 2023, the U.S. Court of Appeals for the Eighth Circuit vacated EPA's 2021 final rule, remanding the matter for further proceedings and reinstating chlorpyrifos tolerances in December 2023. This sent shockwaves through the environmental community. The legal challenge, primarily brought by agricultural groups and the pesticides manufacturer, argued that the EPA's ban was arbitrary and capricious and didn't adequately consider the economic impacts or the availability of alternatives. This reversal threw the entire issue back into uncertainty, allowing chlorpyrifos back onto food crops, at least temporarily.
The rationale behind the Eighth Circuit's decision often centers on procedural aspects, or the EPA's perceived failure to adequately justify its scientific conclusions or economic impact assessments within the specific regulatory framework. It's not necessarily a scientific refutation of the harm, but rather a legal judgment on the process of the ban. And so, in December 2024, the EPA proposed yet another new rule that would ban most uses of chlorpyrifos on food, but with exceptions for 11 specific feed and food crops. This ongoing back and forth highlights the incredibly complex scientific, legal, and political challenges in regulating this chemical. It's a constant tug of war, with public health on one side and agricultural economic interests on the other.
This long history clearly demonstrates that the regulatory landscape is anything but stable, and it's heavily influenced by changing administrations, court challenges, and the continuous generation of new scientific data, like the UCLA study we just discussed. It's a testament to the persistent advocacy required by public health groups to keep pushing for stronger protections, and also to the resilience of industry and agricultural sectors in defending their interests.
Given this turbulent history, it becomes even more critical to understand who exactly is most at risk from chlorpyrifos exposure. The UCLA study, with its focus on residential and workplace exposure, already gives us some clues, but we can delve deeper into the specific populations that bear the brunt of this chemical's impact. It's not just about proximity to fields, it's about the various pathways of exposure and the unique vulnerabilities of certain groups.
Absolutely. First and foremost, we're talking about farm workers and their families. They face direct exposure through multiple channels, mixing, handling, and applying the pesticide itself. They're also exposed when they enter recently sprayed fields, sometimes before re-entry intervals have fully passed. Beyond direct contact, they're vulnerable through spray drift, where the chemical is carried by wind to nearby homes and communities. Contaminated drinking water is another concern, as is the residue carried home on clothing, which then exposes their families, including children. This multi-layered exposure creates a significantly elevated risk for these communities.
And it's not just the direct occupational exposure, it's the systemic nature of the risk. Many farm worker communities are low-income communities of color, and this disproportionate exposure to hazardous chemicals raises significant environmental justice concerns. They often lack the resources or political power to effectively advocate for themselves, making them particularly vulnerable to the health impacts of pervasive pesticide use. This isn't just a health issue, it's a social equity issue as well, where certain populations bear an unequal burden of environmental contamination.
Another group with heightened vulnerability, which has been a major focus of the regulatory debate for years, is children. Children are particularly susceptible, especially in utero and during early childhood. Their brains are still rapidly developing, making them more vulnerable to neurotoxicants like chlorpyrifos. They also have a reduced ability to detoxify chemicals compared to adults, meaning the chemicals stay in their systems longer and can do more damage. This is a critical factor that often gets highlighted in studies concerning developmental neurotoxicity.
And the scientific evidence backing this up for children is quite robust. Studies have linked prenatal exposure to chlorpyrifos with a range of developmental conditions, including lower birth weight, impaired mental and motor development, lower IQs, and increased risks for ADHD and autism. These are not minor transient effects, they are long-term, potentially irreversible impacts on cognitive function and neurological development. Furthermore, children experience greater exposure relative to adults because they consume more fruits and vegetables and water for their body weight, and they frequently put their hands in their mouths, leading to higher ingestion of residues.
Then we have residents in agricultural communities who don't necessarily work in the fields. People living near treated fields can still experience significant exposure through toxic spray drift, even if they don't directly handle the pesticide. The wind can carry it for miles, contaminating homes, schools, and playgrounds. This bystander exposure is harder to quantify, but is a very real concern for environmental health advocates. And finally, of course, manufacturers and applicators involved in the production and application of chlorpyrifos also face occupational exposure risks, though often with more protective equipment and training than typical field workers.
So, when we look at the totality of this information, the strong scientific evidence from the UCLA study, the clear biological mechanisms, and the identification of vulnerable populations, it really begs the question, why is this chemical still in use, even in a limited capacity? This brings us to the crucial exercise of steel manning both sides of the regulatory debate, ensuring we fairly represent the arguments of those who advocate for a ban and those who argue for continued use, even with restrictions.
Let's start with the case for banning or significantly restricting chlorpyrifos, which is championed by public health and environmental advocates. Their argument is multifaceted and quite powerful. They contend that a substantial and growing body of scientific evidence, including this recent UCLA study, definitively links chlorpyrifos exposure to severe neurodevelopmental harm in children, and now an increased risk of serious neurological diseases like Parkinson's. This isn't just one study, it's an accumulation over decades.
They also highlight the disproportionate impact on farm worker communities, often low-income communities of color, framing it as a critical environmental justice issue. This isn't abstract harm, it's affecting real people, often those with the least power to fight back. Furthermore, proponents of a ban point to the EPA's own risk assessments, which have repeatedly identified unacceptable risks, particularly for vulnerable populations. They argue that if the EPA's own scientists have concluded there are unacceptable risks, then regulatory action should be decisive, not delayed or watered down.
And a key tenet of their argument is that no safe level of exposure has been established, especially for vulnerable populations like children. When a chemical is shown to have neurodevelopmental effects at very low levels, the precautionary principle dictates that it should be removed from widespread use. Given the availability of alternatives and the irreversible nature of brain damage or neurological diseases like Parkinson's, they argue that a full ban is not just warranted but morally imperative to protect public health. The long-term costs of these health impacts far outweigh the short-term economic benefits, in their view.
Now, let's fairly present the case against a full ban or for continued, albeit restricted use, which is often put forward by industry in the agricultural sector. They emphasize the immense economic importance of chlorpyrifos for pest control in agriculture. For certain crops, it's considered highly effective against a broad spectrum of pests, and they argue that without it, farmers could face significant crop losses, impacting yields and ultimately their livelihoods and the cost of food for consumers. This isn't a small consideration for an industry that operates on tight margins.
Historically, industry arguments have focused heavily on scientific uncertainty. They might acknowledge some findings, but call for more conclusive data regarding specific causal links and precise exposure levels before implementing widespread bans that could have severe economic consequences. They often critique the limitations of epidemiological studies, pointing out the difficulty in controlling for all confounding factors, such as other pesticide exposures, lifestyle choices, or genetic predispositions, which could also contribute to Parkinson's risk. They might argue that toxicology data from controlled environments is more reliable than population-level observational studies.
They also contend that existing restrictions, such as personal protective equipment for workers, buffer zones around sensitive areas, and limits on application rates, are sufficient to mitigate risks. The argument is that if the chemical is used according to label instructions and safety protocols, the risks are adequately managed. They might also argue that the benefits of its use, particularly for certain crops where alternatives may be less effective or more costly, outweigh perceived risks. For example, if alternatives lead to higher pest damage or require more frequent applications, the economic and environmental trade-offs might not be favorable.
This perspective really highlights the tension between immediate economic concerns and long-term public health. While public health advocates prioritize preventing irreversible harm, the agricultural sector often focuses on the practical realities of farming and the need for effective tools to ensure food production and economic viability. Both sides believe they are acting in the best interest of society, just from different vantage points. The challenge for regulators like the EPA is to weigh these competing interests and scientific interpretations in a way that is both legally defensible and protective of public health.
And that's precisely why this back and forth has been going on for decades. There's no easy answer, and new scientific evidence like the UCLA study continuously shifts the balance of that debate. It adds significant weight to the public health argument, making it increasingly difficult for regulators to dismiss the risks by citing uncertainty. The cumulative data paints a clearer picture, even if some uncertainties will always remain in complex biological systems.
So, to bring it all back to where we started, the March 2026 UCLA Health Study significantly strengthens the evidence linking chlorpyrifos exposure to Parkinson's disease. It's not just another study, it's a comprehensive approach offering both compelling human epidemiological data and detailed biological mechanisms observed in animal models. The fact that it replicates key Parkinson's pathologies in mice and reveals a specific cellular disruption like autophagy in zebrafish really elevates its scientific impact.
The relative risk increase of more than 2.5 times is not just statistically significant, but also clinically significant. This means it's a large enough increase to be meaningful in terms of public health impact. While Parkinson's is a complex disease with multiple contributing factors, including genetics and other environmental exposures, chlorpyrifos is emerging as a specific, identifiable environmental risk that we can potentially control. This moves it beyond a general pesticides are bad statement to pinpointing a particular chemical with demonstrable harm.
And that specificity is what gives us the ability to act. It underscores the urgency of the ongoing regulatory debate. The evidence points to a clear need for stricter controls or indeed a full ban to protect public health, particularly for the most vulnerable populations such as farm workers and children. This isn't about eradicating Parkinson's entirely with one action, but about removing a known avoidable risk factor that contributes to the disease's burden on individuals and society. It's about making informed decisions based on the best available science to reduce preventable harm.
Precisely. It's about acknowledging the very real human cost behind these numbers and the complex regulatory battles. This study provides a powerful new tool for advocates and policymakers to push for stronger protections. It's a reminder that even when we know nothing about a topic initially, digging into the details, understanding the science, and recognizing the human impact can bring clarity to even the most contentious issues.